Hello everyone, my name is Erjun Liu. Today, I will be presenting on matrix concepts with a specific focus on finding the proper square root of the identity matrix. I will cover the mathematical context and the solution I implemented. Let's begin with the fundamentals. A matrix is simply a rectangular array of numbers arranged in rows and columns, serving as a fundamental tool in linear algebra to represent linear transformations. Historically, the term was coined by James Joseph Sylvester in 1850, shortly after Arthur Cayley defined matrix multiplication and the concept of the identity matrix, establishing them as a single algebra entities. While matrices are a broad topic, today we will focus on a specific, powerful type, the permutation matrix. So, what is a permutation matrix? It is defined as a square binary matrix that has exactly one entry of 1 in each row and each column, with all other entries being 0. Conceptually, every n by n permutation matrix corresponds to a permutation of the numbers 1 to n. It effectively represents the action of reordering elements. The simplest example is the identity matrix I sub n, which represents the do-nothing permutation, where all elements stay in their original places. Why are these matrices useful? When you multiply a vector V by a permutation matrix P, rearrange the elements of that vector, but the most crucial property lies in its inversion. For a general matrix, finding the inverse is computationally expensive. However, for a permutation matrix, the inverse is simply its transpose. Mathematically, we say P inverse equals P transpose. This makes them incredibly efficient for computation. These matrices have significant real-world applications. In cryptography, they act as pitboxes in diffusion layers. They mix bytes to create an avalanche effect, hiding patterns from attackers. In graph theory, they are used to check for graph isomorphism. If we can find the permutation matrix P such that A equals P times B times P transpose, we prove that two networks are structurally identical. In quantum computing, since permutation matrices are orthogonal and reversible, they are inherently unitary. This allows them to function as quantum gates, preserving information without collapsing superpositions. Let's look at a specific example relevant to our problem, a 3 by 3 matrix. This matrix shown here swaps the first two rows while keeping the third fixed. This brings us to the concept of involution. An involution is the matrix that is its own inverse. If you square this matrix, meaning P squared, you get the identity matrix I. Mathematically, applying the swap twice returns everything to the start. Now, let's define a task for this assignment. We need to compute the number of proper square roots of the identity matrix, denoted as PSQRID of n. Mathematically, we are looking for permutation matrix B such that B squared equals I sub n. This means squaring it yields the identity, but B is not equal to I sub n. It is not the identity itself. In simpler terms, we are counting non-identity involutions. To solve this, we look at cycle decomposition. For permutation to be an involution, where b squares equals I. It must consist only of one cycles, fixed points, and two cycles, swaps. We let k be the number of swaps. Since it must be a proper root, k must be at least 1. The combinatorics involves two steps. Choose. Select two k elements to be swapped from N. Arrange these elements into pairs. By combining the choosing and pairing terms, we arrive at the final summation formula. We sum from k equals 1 up to the floor of n over 2. The formula reads as the summation of n factorial divided by 2 to the power of k times k factorial times n minus 2k factorial. This formula allows us to calculate the count directly without listing every matrix. Moving to the implementation, the program takes an integer n, where n is less than 21, and outputs the count. My strategy was to avoid brute force, generating all n factorial matrix for n equals 20. It's impossible due to time constraints. Instead, I implemented the combinatorial formula derived in the previous slides. The code relies on two major functions, non-involutions. This iterates through all possible values of k, calculates the term and sums them up. PSQRID. This is the wrapper function. Crucially, it takes the result and subtracts 1. Why subtract 1? This removes the case where k equals to 0, which corresponds to the identity matrix. This is ensure we satisfy the proper requirement. Finally, here are the results. For n equals 4, the code correctly identified 9 matrices. For n equals 20, the code was able to efficiently calculate the massive result, which is approximately 23.7 billion proper square roots. And these are the references I use for the historical context and pictures. Thank you for listening.